Hello physicists, welcome to our March 22nd edition of physics. I am joining you here from my unlit office, partially because I don't like the hum of the fluorescent lights, and also because last night I went out camping with the fam and my eyes are still pretty sleepy. All right, so let's talk about a couple of things. Today should be a short video because we're not doing anything new, not much anyway, and I just want to make sure that we're all okay for the homework, which I would like you to have done by Wednesday. Okay, on our quiz, we had quite a spread of scores. 83% is lower than I would like. The one that I found most confusing as one that a couple people got wrong was this one, where I asked for the units on momentum. My idea is that this is an open note quiz, so if you know that J is the force times the time, it's the amount of force that you're applying over a length of time, then that should be newtons times seconds, which is kilograms meters per second squared, times seconds, and then one of those seconds cancels out, and it's just kilograms meters per second. Notice also that that's the units on momentum, kilograms meters per second, and there you go. Now, I'm guessing that the newtons over seconds might have just been some people looking at this and saying, force times time, Newton seconds, but not take enough care. That's my guess. This one I was a little concerned about. I was surprised that we got such a bimodal sort of distribution. And let's say that in this problem, you define this direction to be west. You've got car A has a mass of 2m going at 20 meters per second, and car B has a mass of m, and it's going 30 meters per second. And this is a conservation of momentum problem, so the idea was that you go ahead and take 2m times 20 meters per second plus m times 30 meters per second. Okay, you're just adding up the mass times velocity plus the mass times velocity, and it's okay for me to choose west as the plus x direction because they're both moving in the same direction, and I don't need to worry about the sign. There's no sign difference between these velocities, and that equals the total mass once they stick together. So 2m plus m is 3m times this velocity of both of them stuck together. So I can easily do that because that's 40 plus 30 would give me m times 70 meters per second. I divide both equals 3mv, and now I divide both sides by 3m, and what I get is 70 over 3 meters per second equals v. Now, 70 over 3 is 23.3 meters per second. And so the correct answer is that none of the above answers were correct. But I have to admit, Bryn today in class brought up the good point that if you think about sig figs, and consider this as only having one sig fig, 23 meters per second looks a lot like 20. So I had to concede that point, and I said, okay, those 6 of you who had this as the answer, I will give you those points. Okay, so I did that. I did that on Canvas right before this, before I recorded this video. You can see I'm tired. So go ahead and if you were one of the people who responded to this, make sure that I actually did give you your points. Okay, so today we're not going to do a whole lot of new stuff. We're just going to go over some ideas from last week. Remember that momentum is a vector, so it can have a sign. It's almost like velocity, but it has an extra mass component. So the bigger your mass is, the more momentum you have. And last week what we said was, notice that how you can write F equals ma by taking the time derivative of that. We assume that the mass is not changing for your particle, and this net force then is the thing changing your momentum. And because that's true, this also can be applied for an entire system, and you can add up all of the forces acting on the particles, and that will be what changes the net momentum of your system. So the net momentum is if you take the m times v vector and add all those up for your entire system. So this F net is where you add up the total force on every single particle. And keep in mind that we learned last week that if you don't have any external forces and you just have the objects bouncing off each other, acting under the influence of just their own forces, that F net is going to be zero because of Newton's third law. Now here's a homework problem that I gave you on this. I'm mentioning this mostly just so that you don't do too much work on it. Not force times distance type of work. I mean like effort. Okay, so this one has a big olive lies at the origin of a coordinate system. So there it is. X of big olive equals 0, 0. X of all, or let me call that R. R of olive equals 0, 0, and F on that olive equals 2, 3 newtons. So this is meters, this is newtons. And so it's getting pulled on in basically that direction. And then on the other hand, you have a big Brazil nut lies at 1, 2, so that's going to be up here. 1, 2, 1. So our R of our Brazil nut is 1.0, 2.0 meters. And at time equals 0, what's the force on this one? It's going to be minus 3 over 2. Minus 3 over 2. Okay, so they're going to kind of be pulling in different directions. This object's going to go, the olive is going to go one way, the Brazil nut's going to go the other way, but they're not exactly the same mass and they're not exactly going in opposite directions, so this isn't going to quite cancel out. Okay, so what it's asking is, in unit vector notation, what is the displacement of the center of mass of the olive nut system at t equals 4 seconds with respect to its position at t equals 0? Now, something nice about this problem is that it's just asking you the displacement. That's this. And so you don't actually have to calculate the initial position of the center of mass. You just know that it's going to follow this type of a rule. And it's going to follow that type of a rule in the x direction and in the y direction. And another nice thing about this problem is that the initial velocity of both the olive and the Brazil nut is 0. So all you have to do in this problem is go ahead and find the F net, okay, which is going to be, you have your F on the olive, this is the F on the olive, and F on the Brazil, and the F on the Brazil is this, there it is, minus 3 minus 2 newtons. So it's going to be F on the olive, and we're adding these as vectors, so that means you add the x components and you add the y components, F of the olive plus F of the Brazil nut. Okay, that's the net force on your system. And now you use F on your F net on your system equals mass of your system times the acceleration of the center of mass. And that acceleration is also a vector. This m is going to be the sum of the masses of the olive and the Brazil nut. So that's going to be 0.5 kilograms plus 1.5 kilograms. Okay, and so what all you have to do in this problem is find out what that acceleration vector is. So F net is a vector because you're adding the x components, you're adding the y components. Then you divide the whole thing by the total mass. That gives you the acceleration of the center of mass. And then to find the displacement, if you want to find the displacement of x, that's just going to be 1/2 ax t squared. T, of course, they're asking us to find the center of mass at t equals 4 seconds. And the displacement for the center of mass in the y, ay t squared. And of course, this is the acceleration of the center of mass that we're talking about, not the acceleration of each one of these particles, which you would get just from F equals ma for each one of them individually. All right, so there's nothing too profound about this. The other big thing that we did last week was talking about the impulse momentum theorem, where if you push on an object for a short amount of time, could be a short amount of time, could be a long amount of time, doesn't matter. In any case, the impulse that you apply to an object will determine the change in momentum of that particle. And if you think about it, the reason this is a good update to our language, we in chapter 8 had just been talking about energy and work, and that's not a super way to get a handle on what's happening when an object changes direction. Because if I have an object coming this way and I push on it, I'm doing negative work on it because I'm going to be slowing it down. But then, as soon as it goes to stop and turn around, all of a sudden I start doing positive work on it, and that makes it speed up. Now, there's nothing contradictory about that exactly, but it does give you sort of a weird feeling in your belly when you think about work being negative for the first moment that a bat hits a ball, and then it becomes positive for the last moments that the bat hits the ball. On the other hand, with impulse, the impulse is always just in the direction of the force. So if you have a force of a bat hitting a ball, it's always just pointing that way. The thing that's changing is the momentum of the ball is going from this way to that way. So you're going to have a bigger change in the momentum because the momentum has a sign of the velocity in there. And so in that way, it's a little more intuitive. At least that's my that's my feeling. It's more intuitive, even though you have to deal with the extra clutter of working with vectors. Okay, so here's a quick example of an impulse momentum theorem. I just give it to you because I expect that you'll see this type of question on your test in a couple weeks. It says a football of mass m initially at rest is kicked so that I don't think I wrote this correctly. Is kicked so that leaves the foot at speed v. This was speaking caveman when I wrote this last night. If t represents the duration of the collision between the ball and the foot, which one of the following expressions determines the magnitude of the average force exerted on the ball? Well, you're given the mass of the ball, you're given the final speed of the ball, and you're given the time. And they want to ask you, what is the force? Well, this is just impulse momentum theorem 101, because force times time equals mv final minus mv initial, but that's 0. So in this case, your force, your average force, is just mv over t. All done. Easy. No problem. Okay, so the more tricky problems that we did last week all had to do with momentum conservation. Some of them had to do with, you know, shooting a bullet into a block, or having two balls knock off each other. We talk about elastic collision, where the sum of all of the kinetic energy of your objects in a system before the collision stays the same as the amount of kinetic energy in all your objects after the collision. A pool table works approximately like that. However, the kinetic energy of each object changes over the course of the collision. On the other hand, the more common more common thing to happen is an inelastic collision, where, you know, a truck hits a car, or a brother hits a sister, a father hits a son. It's a mean world out there. And in that case, you don't have the same amount of kinetic energy before and after. Now, let's just take a look at a couple of your homework problems to make sure that you know how to do these. All right, so in this problem, we have a cart with a mass of 340 grams moving on a frictionless linear air track with an initial speed of 1.2 meters per second. Okay, so that's our M1. That M1 has a mass of 0.340 kilograms, and it has a V1, and let's put an initial on there. V1 initial, because it's going to knock into something and change its speed, 1.2 meters per second. It undergoes an elastic collision with an initially stationary cart of unknown mass. After the collision, the first cart continues in, okay, so it starts going out this direction, and it hits M2, which is just sitting there. And M2, we don't know. I don't need an M1 initial. The masses are not changing. That's just M1. M2, you don't know. Question mark. V2 initial, you actually do know. 0 meters per second. Initially stationary cart. Okay, so that's your before. Now your after is going to be a situation where your M1 is going more slowly. Same mass, different speed. So this is your before, and here's your after. And in this case, the V1 final, they give you as 0.66 meters per second. The M2 presumably is speeding off in this direction, and it has now some V2 final that we don't know. Now, for some, we might at first say, oh no, because if I've just momentum conservation, they're all just moving along a single direction. I don't know the mass, and I don't know the final speed of the second ball or the second cart. And so if I just had momentum conservation, I couldn't do the problem. However, they give us the piece of information that this is an elastic collision. And because it's elastic, it means that I get an extra equation. I get my, if I add together the kinetic energy of the first ball plus the second ball, it equals the kinetic energy of the first ball plus the kinetic energy of the second ball afterwards. Okay, so in physics, at least with my physics brain, what I'm thinking is, oh, I'm done with this problem. I have two equations, I have two unknowns. From here on, it's just math. Okay, so all I have to do is I say M1 V1 initial equals M1 V1 final plus M2, this is my M2 V2 final. So that has two things I don't know, M2 and V2 final. Why don't I have this second term from the M2 V2 initial? It's just because this is 0 meters per second, so I don't need to put it in there. And the same is going to be true for my equation for M1 V1 initial squared. This is your kinetic energy before. That object doesn't have any, the second one doesn't have any kinetic energy beforehand. And then I get 1/2 M1 V final, V1 final squared, plus 1/2 M2 V2 final squared. So all I would do in this case, these are the two that you don't know, so you have to come up with one equation where you can solve it. What I would do, it asks first, what is the mass of the second cart? Okay, so one thing that you could do, for instance, is solve here for the speed of the second cart in terms of all this stuff, stick it into this equation and find the mass. Okay, because then you could get rid of your V. You could solve by substitution. There are many ways to do it. Also, I will just tell you, if you don't feel like doing the algebra and you think you can get away with it, they do have some examples of equations where they've already worked everything out in your book for you. So if you want to do it that way, I won't stop you. Okay, it's kind of the same idea in this other homework problem that I gave you, where you've got two titanium spheres. They approach each other head-on with the same speed and collide elastically. Okay, so you've got M1 V and M2 with a minus V. After the collisions, one of the spheres, whose mass is 300 grams, remains at rest. Okay, so let's, if I set it up this way, well, yeah, I mean, you can do it however you like. I might do it like M1, M2, and then this speed would be V equals 0, and the M2 then would be 0.3 kilograms. Okay, and the question that they ask, and presumably this will go off at one direction or another, we don't really know. And it says okay, what is the mass of the other sphere? So this looks like a problem where there's a lot that we don't know, but again, there's really only two things that we don't know. We don't know V, and we don't know M1. Okay, what is the speed of the two spheres' center of mass if the initial speed of each sphere is 2 meters per second? Okay, so this is 2 meters per second. Here my V is minus 2 meters per second. Okay, and I will let you puzzle over that again, but it's essentially the same idea. If you have any questions about it, just email me and I'll try to get back to you. Okay, now. So what we've been doing, we've been adding up the momentum in one direction and saying the sum of all that momentum, barring any external forces from my system, is going to be conserved before and after an interaction. Now the nice thing is this actually also works in 2 dimensions or 3 dimensions more generally. And here in your book, they give a nice example where you have at the beginning like a billiard ball, and here's something like a cue ball, and this one comes at the other one. And you choose your coordinate system such that it's just going to be going along the x direction. And so the momentum conservation in this particular case looks just like M1 V1 initial That's just the momentum in the x direction of this. So this is your x direction equation, and you have a y direction equation. The x direction equation just involves the momentum in the x direction. The initial momentum in the y direction is 0 because this ball isn't moving, and this one only has a velocity along the x direction. Now, then, once the balls scatter off like this, you have your m2 and m1 as in the picture, and in your x direction, both of them have a component that's positive, and so they both get that m1 v1 cosine of angle. All you're doing is, doing your normal vector stuff, where this would be v, and this component, the y component would be v sine theta, and the x component would be v cosine theta for that particular way of drawing it. For your y direction, one of them is going to be negative, and that has to be so for the total momentum to be 0. So they are moving in the y direction, but the total momentum, so the m2 times vy equals essentially m1 times vy in the other direction, if we were just talking about speeds. If you're talking about the speeds, that y component of the momentum for each one are going to be equal but opposite in direction. And then if the collision is an elastic collision, you get an extra piece where the kinetic energy of this plus 0 equals the kinetic energy of that and that. So you add up the kinetic energy afterwards equals the kinetic energies beforehand. Now, I only gave you one homework problem on this, and it's sort of the most bare bones problem that you could possibly get. You've got a VA, a VB before a collision. You've got a VA, VB after the collision. I don't know what VB final is, but it's going to be a vector. It's going to have an x component and a y component. And what does my momentum conservation equation look like? Well, it just looks like MA VA initial plus MB VB initial equals MA VA final plus MB VB final. And notice what this really is talking about is that this is a vector sum. So this mass is a scalar, so it gives you MA equals MB equals 2 kilograms. But it wouldn't need to be that way, but it does simplify this problem quite a bit. And essentially then what you would find is it first asks you to find what's the final velocity of B. Okay, well, if you want to find the final velocity of B, all you have to do is subtract this off and divide by mass of B. So 1 times MB times MA VA initial plus MB VB initial minus MA VA final equals VB final. Okay, so there's an x component to this, an x component to this, an x component to this, and put all those in here, and that's one number. And then you put in the y component and the y component and the y component, and that gives you a different number. And so your answer in this is going to have the form Vx Vy meters per second. Okay, and that's what your VB final in your homework, or you can write it in terms of Vx times I plus Vy times J meters per second. That's also nice. Okay, either one of those ways I'm happy with. Then the second part asks, what is the change in the total kinetic energy? Well, you might have to think for a second, but if you have a VA, okay, that's a vector, and it has a VA x component and a VA y component, the kinetic energy is 1/2 mv squared. But I know from Pythagorean theorem that if I wanted to do that, another way I could write that is 1/2 m VA, VAX squared plus VAY squared. Okay, so when it asks you what's the total change in kinetic energy, what you're going to have to do is add up 1/2 MAVA initial squared plus 1/2 MAVB initial squared. Okay, that's your initial kinetic energy of A, initial kinetic energy of B. And then you're also going to have to find your final 1/2 MAVA final squared plus 1/2 VB final squared. Okay, so this, and we don't know that they're equal. Okay, it's going to be less than or equal to that initial. But I want you to calculate this, calculate that, and then take the difference between them to find the total change in kinetic energy. Okay? All right. So, I don't know if you find this stuff interesting or not. I do want to say, though, it does have some interesting consequences. And one of the interesting consequences is that if you can think about the energy and the momentum of these particles, you can start to do some real banger experiments. So, for instance, in the early 20th century, Rutherford discovered the nucleus of the atom by shooting alpha particles, which are basically helium nuclei, at a very thin sheet of gold. And because he was able to look at the momentum change of those particles, he was able to infer a lot of things about the gold foil. Now, in a more sophisticated way now, there are these enormous experiments that continue to be ongoing where you take a proton and another proton and you spin them around in really huge rings and smash them together. And the idea is that a different particle is created and it's very quickly decays into all sorts of other particles. And by tracking back the total energy and momentum of those other particles, we're able to infer the particles that have been created in the center. So just to give you some idea of the scale of this type of experiment, here's our biggest experiment in Louisiana, which is truly a world-class experiment. It's something that we should be very proud of having in our state. It's the LIGO Observatory, where there are these 4-kilometer-long arms, and they send the light down basically interferes. The light interferes with the having gone back and forth many times with these very carefully positioned circular mirrors, and that's a very impressive feat. But it's also not quite as big as what is over in Switzerland. That's the biggest physics experiment in the world right now, and they have about 27 kilometers. It goes over the national border between Switzerland and France and comes back, and that's the size. Right now, they're agitating to build a super LHC where they're going to have a 100-kilometer long ring. Which, if you think about it, to have 100 kilometers where you have a very high vacuum, all surrounded with superconducting magnets, it's quite a project. I don't know that they're going to get it made. What can I say? I wish them luck. But what they're doing now at LHC looks essentially like this. So here's your detector, and your detector doesn't exactly, it can't observe the smashing of these two ultra high energy protons, but what it sees instead is the spray of all of these particles off. And you notice that they're bending. That means that they're in a big magnetic field. We'll learn about that next semester. But by tracking back all of the energy and momentum of those particles, they're able to infer the existence of short-lived particles at the center. So for instance, here at CMS, here's an experiment that I saw a notice about when I just Googled this. You'll see that they're looking for events from the decay of a Higgs boson to two photons. Okay, so from the Higgs boson to light particles. And what they do is they look at all of these particles, they add up their energies and momenta, and are able to find a little bump there, and that's little bump they eventually infer is the source of the particles, which is the Higgs boson. Okay, so it's rather indirect. Okay, so that's sort of an interesting thing. You don't have to, know it for a test, but it should hopefully give you some background about why the hell am I interested in this. Okay, another thing that's sort of interesting is the idea of using momentum conservation to get a rocket going. And you can imagine if you're in deep space. Now, I linked to a video that gave a little bit more of a complicated scenario where you're sitting on Earth. But now, just imagine you're already in deep space and you want to speed your rocket up. How do you do it? Well, essentially what you have to do is you have to push particles out the back really fast. And what this equation is saying, they derive this in your book, but I just want you to appreciate what its content is. It says the V final minus V initial. So this is how much have I sped up my rocket by throwing stuff out the back. It depends on the mass initial and mass final of my rocket. So if I have to put out mass out of the back because the momentum that way is going to be compensated by the momentum this way of the rocket. So if I'm going to get going, I have to shoot momentum out of the back. Okay, so you've got to fart out exhaust. And it also depends on the relative speed of that rocket fuel to the rocket. So the faster you're pushing out that exhaust, the faster you're able to go forward with your rocket. Okay, so this is kind of the ideas of some of the things that you can use this for, and I'm going to stop there and just say it again. Momentum conservation can be applied in 2 dimensions or 3 dimensions. You just add up all the momentum in one direction or the other. These sorts of considerations of energy and momentum are used in fundamental physics, for instance, finding the Higgs boson or any other type of exotic particles. And furthermore, if you think about momentum conservation, that gets you a long way towards the possibility of doing some rocket science. All right, so thanks for watching. Remember, homework is due on Wednesday.